Hello, my name is Dogalil. In this talk, I will briefly explain the algorithm presented in the paper, a framework for benchmarking class auto-distribution detection and its application to ImageNet. We recommend understanding the background and motivation for this algorithm first by either reading the paper or watching our full presentation. The link to the paper's presentation can be found in the description of this video. The algorithm is fully explained in the paper, and we encourage you to read it. The algorithm can be divided into 4 steps, which we will go over one by one. First, the algorithm receives samples from OOD classes. In the case of ImageNet, as demonstrated in the paper, this OOD data consists of all classes in ImageNet 21K that are not included in the standard ImageNet 1K. Next, the algorithm splits the samples for each class into 2 sets, an estimation set that will be used to estimate the detection difficulty for this class, and a test set that will be used for the final evaluation. The second step is to iterate over all OOD classes and to estimate the difficulty for each. Detecting performance is evaluated by ranking OOD classes lower than in-distribution classes. Therefore, the difficulty of an OOD class, which we call its severity score, is simply the mean confidence score given by the confidence function to all samples in the class's estimation set. In this example, the Viceroy butterfly class was estimated to have a high mean confidence score of 0.98 based on its estimation set, which means it's hard to distinguish from in-distribution classes. The flashlight class, on the other hand, was estimated to have a low mean confidence score of 0.01, which means it is easy to distinguish from in-distribution classes. The third step is to sort the OOD classes by their severity scores in ascending order. Since the Viceroy had a high severity score, it would likely be towards the end of the array, while the flashlight with a low severity score would probably be towards the beginning of the array. We group the OOD classes into groups with increasing severity by using a sliding window. The size of the sliding window is set to be the number of in-distribution classes to be evaluated. Next, we choose the groups that correspond to different percentiles from the array of sorted groups. Finally, we construct the class auto-distribution benchmark for each severity level X from the set of test samples of all classes in group X. This procedure for choosing groups allows us to interpret the severity levels using percentiles. For example, severity level 5 contains classes that match the median severity among the considered groups. Thus, the performance evaluated on the benchmark for severity 5 corresponds to the performance of the model on samples with a median detection difficulty. This is how our algorithm generates the benchmarks used to evaluate class auto-distribution performance in our paper. For more information, we invite you to read our paper.